nanohub.org.
You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
All right. So this is lecture 5 on energy bands, and today is a very interesting lecture in the sense that today at least finally we'll be solving a real problem. It's not real yet, but it gives a lot of information about the real thing we eventually want to know about. So we'll start by talking about how to solve Schrodinger equation in periodic potential UX. Now remember why we want to solve the Schrodinger equation to begin with, because as I said, not all electrons participate in the conduction process equally. So if you want to know the resistivity of a material, then in that case we'd like to know which fraction of the total electrons are actually taking part in the conduction, are available for conduction. So in this case, we want to know where the electrons sit to begin with, and then subsequently we'll figure out what fraction of them moves. And the periodic UX, well, because it's crystal, and in a crystal, we want to solve the Schrodinger equation to see where energy levels stay within a crystal. And then we'll talk about a set of other things. Now, this is again the problem that we had been talking about in the last class as well. And this is a problem where the red electron is sort of swimming through a series of ions, or the core or the nucleus, and they are being periodically pushed and pulled by these respective positive charges, and the electrons are of course negative. So, and what we did in the last class in solving the toy problem, we assumed the atoms are so far apart that we can just take one of them. Don't worry about the neighbors, and just take one of them, say where they are, if they are very close to the bottom or way up in energy, how they transmit and where they stay. But of course atoms are not far apart. They are only 5 angstrom apart, or less than in many cases, maybe 2 angstrom apart. They are not far apart. So in this case, it is impossible to neglect the effect of the neighbors. And that is essentially the essence of this problem that we are going to solve. Now let's consider this full potential in a simplified way. Remember again, the reason we write it as a square potential going up and down is because it's an idealization. In practice, it will be like a series of Coulomb potentials. You remember this hyperbolic type relationships, and they will 1 over r type relationships, then they will sum up. But this is an idealized version just for simplicity. But it will give us many information which will be correct also in real crystals. Okay. Now this is UX, goes up and down in position. Now if you look at the period, let's define them. A is the bottom of the well, so let's sort of the extent of the atom, let's say. And the B is a barrier between them. And the period then therefore is A plus B. We'll call it P. Remember, this is not momentum. This is for this case just a distance, maybe 5 angstrom from one atom to another. Now you see something funny here, that I can of course solve for the Schrodinger equation here in one shot. If I take an energy which is below UX in that shaded region, as you can see, then when the energy U is higher than K energy, then you know how to write the solution. E to the power alpha x plus e to the power minus alpha x. That we have seen in the last class. What should we do when the energy is above the potential, in the white regions in between? Well, we'll write it as sine kx and cosine kx. And remember, I have to know which white region I am writing at. So I put a little index n plus 1 just to say that this is next to n region. So I put an index. So, for every set of pair of these potentials, there will be 1, 2, 3, 4, and so on and so forth. So I have a series of solutions. Now, if you didn't know anything else, then and simply applied what I told you last time, that is, take a boundary condition at plus infinity, another at minus infinity, two unknown constants gone. Every interface match the wave function, match the derivative, right? Then you can essentially solve this problem, no problem. But you can immediately realize that even in a centimeter cube of material, even in one dimension, there are probably 100 million atoms sitting. Now you have to solve 100 million multiplied by 2 equations. Now the boundary condition may give you 2 less, but that's not really helping you. So this is an impossible problem to solve, and there's no way then in 1940s, when these problems were actually solved, you could possibly solve it. There was no computer. But it was of course solved that time, and this is how. And what helped the solution of this problem is this beautiful theorem called Bloch theorem. We'll not prove it or anything, but just show you the content of the theorem, that how it solves it. It's very simple, you'll see. Now remember the 4 steps. There are 5 steps of both solving for the energy and the wave function. The first 4 were determining the eigenvalues of the energies. Now we write the same equations, but as I just explained in the previous slide, that if I just use this rule blindly, too many equations cannot solve it, and therefore I cannot know where electrons sit. What I can do instead is, instead of using 2 and 3, we can replace it with something very simple, using the fact that this is a periodic potential. It's not any arbitrary potential. Things repeat, and that information we should be able to use somehow to reduce this humongous problem to something that you can solve essentially in 15 minutes. Now, remember where that comes from, or see how it comes from. So the main feature of this potential is that if you take any given location ux, position x, and potential corresponding to that ux, assuming that x equals 0 is the origin on the left, and that can be any arbitrary origin, then you can see that when x is displaced by a plus b, the potential is the same. It's one period away, and I'm, instead of a plus b, I'm writing just p in order to save some time. Now, if the potential is the same, then although I don't know the solution yet, I don't know the solution of the Schrodinger equation, but I could say this, that whatever be the solution at location x, the solution at location x plus p must be the same. Remember the definition of this Bravais lattice and the periodic solid, that every point you sit looks around you is exactly the same as every other point you sit. Now, if every point you sit looks exactly the same, the solution, whatever it is, we do not know, whatever it is, that must also be the same. So if that is the same, so therefore I can say the probability of finding an electron at a given location is exactly the same as it is one lattice site away. What does it say about the wave solution itself, the psi? You see, this is psi squared. What about psi itself? Well, psi, you can see, the wave function, is almost the same, except I'm allowed to have a phase factor e to the power ikp. Again, p is not a momentum, it's a distance. Why ikp? Why is the same? Well, if k was 0, no problem, right? On both sides, I have the same thing, square it, no problem. But remember, this is an absolute value squared. That means it's a complex conjugate, psi star. And so when I have psi star, then obviously on the right hand side, I will pick up a minus ikp. And when I multiply them two, then of course, this ikp, e to the power ikp, will go away. So therefore, the solution on the proposition on the left hand side, that the probability of finding an electron is the same, one lattice site apart, implies that the actual solution, one light side apart, must be given by this wave function multiplied by a phase factor. You see? So take this, this is an important step, and so you should try to understand that clearly. Okay? And this is also, by the way, this is k is not this h square k square divided by 2m as we saw before. This is just a number k, because k could be anything. I could multiply with anything, and when I multiply with complex conjugate, anything I put, it will always go away. So k doesn't have to be any specific number. It will be in a second, but that's not the old k. Okay, so now let's use this information, see how it works. I just told you that if I know the solution psi x at any point, if I knew, then at x plus p distance away, the solution will be related to each other by the relationship shown in the bottom. You can see at x plus p, it is simply one phase factor shifted for the original solution at x. Well, if this is true, then isn't this true as well? If I wanted to go two step, not one, then the second step, I could relate back to the first step. And I could write that psi at twice the step is simply psi at the first step multiplied by the one phase factor. Right? You see this? And if the first one is already known from the left hand side, you can see. And therefore, this I could write. Do you see this? That when I have gone two steps, I could cascade the solution back and essentially pick up the phase. So if I am two steps away, I will pick up a phase factor compared to the first one, 0th one, is by 2 kp. So you can see that if I am n step away, and n could be a billion, if I am n step away, I don't know anything else, but obviously I could say this n step away, this statement should be obvious. Because what I am doing here, you can see I have picked up a phase factor which is kp, of course, but now multiplied by n. So I have n phase factors, and this you can see where it came about. The n was connected to n minus 1, n minus connected to n minus 2, all the way folded back until you hit 1. And that's where you picked up all these phase factors. Well, I haven't done any solution yet, but simply I'm setting up the problem, and in the next 3 or 4 slides we'll see how to use this information to solve the problem. This is something replacing the boundary conditions, you see. Continuity of the wave function and the derivative of the wave function, that is something we'll use on top of this equation. Now, let's look at this and then say the following statement. Now, this part is not obvious, and this is sort of one of the tricks, and we'll see how it works, but I will explain it later on. So assume you have taken this string of atoms. Now you pull it back. Now how do you pull it back? In real crystal, you couldn't possibly take the atoms and pull it back in a string, right? So in principle, you couldn't do it. But what you are telling here is that when the atoms are so far apart, let's say 1 and a million, unless the atoms are very close to the surface, in between, you know, one side you have a million plus 20, another side you have 100,000 or something, it really doesn't matter what you have at the very end because it's so far away. So therefore, whatever you do, pulling it back, twisting it, whatever you do, it's not really going to change the solution inside. Of course, we are not going to know that unless we begin to compare with the experiment later on, that whatever we did, this is correct or not. But for the time being, we'll proceed, and then we'll come back and see whether the solutions are real or not. Now, if I pull it back, then what will happen? You see, so I'll start from 1, 2, 3, go all the way, but now the n minus 1, the nth one is again the first one. And then 2n1 is again the first one, you see. So this, because it's a periodic boundary condition, that's what they say. In that case, what should happen? Well, in that case, you can say that if the nth one is exactly equal to the first one, then psi x plus np should not be just a phase shift away. It's the original thing, because on the left hand side I should be able to replace this with psi x again, because it's the first one. And if the first side, left side and right hand side has to be equal, then you can see then e to the power I k p n, that must be equal to 1, only when I pull them back together. And if it is 1, then you know that this 1 equals e to the power I 2 pi n. Do you know this formula? This is, so I can set these two things equal, because every time something is twice the multiple of pi, 2 pi, and when it's to the power I, and in that case the result is always 1, you know, because it's like 360 degrees coming back and coming back again. And so I can write k equals 2 pi n divided by np. Is this true? Do you see that? If you look at the exponent on both sides, left and right, and divide both sides by np, then you can see that these solutions are correct. It satisfies the solution. What does it tell you? What it tells you is that any arbitrary value of k is not allowed. If the potential is periodic, remember the phase factor I had, e to the power kp. Now, any arbitrary value of k will not occur. If it has a periodic boundary condition, then it must have 2 pi n divided by np. Now, little n, it could be 1, 2, it could be minus 1, all the way to n over 2. Why could it not be n plus 1 over 2? You can put it over there and you can show that that's exactly equal to 1. 1 again. The value is 1 again. Another thing I want to point out, that there is this solution of the k that has two sides, positive side 0, 1, 2, 3, 4, and a negative side 0, minus 1, minus 2, minus 3, so on and so forth. What does it mean? The plus 1 means, remember, e to the power plus ikx, wave going in one direction, right? Positive direction. E to the power minus ikx was, what was it? Wave going in the other direction. So this is like wave going on the ring in one direction, that's e to the power ikx, wave going in the other direction, e to the power minus ikx. Of course, both solutions are fine. Electrons could go in either way. And that's what the positive and the negative strings mean. Okay, so we are getting there. Not yet, but getting there. Remember, any arbitrary value of k is not allowed. Only certain values of k are allowed. Okay. What is the maximum and minimum value? Well, we can see what is the maximum. The maximum would be when little n is equal to capital N over 2. And if I put it over there in the equation, I will see pi of divided by p, and on the other side minus pi over p. That means all my solutions, whatever they are, cannot exceed this boundary. I don't know what the solutions are, but it cannot exceed this boundary, and later on we'll call this Brillouin zone, because this is where all the solutions of the eventual equation, this is where they live. Okay, now finally we are able to solve the problem. Let's see how it works. Do you remember the solution that I have on the left hand side of 0, 0 to minus b, sine beta x and cosine beta x? Now on the right hand side, between 0 to a few slides before, what did I write? E to the power alpha x plus e to the power beta x, right? Minus alpha x, remember? I'm here instead writing in terms of sine and cosine. Is this right? Well, if it is, if this is equal to an imaginary quantity, then it's fine. Sine and cosine will be fine if we want to write it e to the power alpha x with the exponent alpha and beta in terms of imaginary. It could be real or imaginary. In that case, writing in this particular form should be fine. You should check this out just by inserting the equation. You see the definition of alpha and beta above. You should check it out yourself, that this is exactly the same as I said before in terms of e to the power plus alpha x and e to the power minus alpha x, exactly the same. Now, let's use the boundary condition. First, on the green line or the blue line. I'm not colorblind yet, but So the blue line, and what do I have to solve here? Match the boundary condition. I'll have to say wave function is continuous and its derivative is continuous, right? Okay. So I know the two solutions. I should be able to do it in a second. So at x equals 0 minus and 0 plus, I can say the continuity of the wave equation and its derivative. And I will not labor you with this statement that b sub a equals b, capital B sub b, because you can see if you insert x equals 0 in this particular equation and let the wave function be continuous, that's the relationship you're going to get. Okay. The other thing is, well, then I should have to go to the other side, because now I have to match the boundary condition at x equals a. Then I'll be done. But you can immediately see there is a problem. If I need to go to the other side from 0 to a and need the information from the other side, then in order to know that the information at a plus, I will have to then solve the next atom. Then I'll have to use that information. In order to get that information, I'll have to go to the neighbors, and I'll have to keep going to the right. Now this is not good. What I want to do instead is the information we just collected, that the wave function at x equals a, what is it equal to? The wave function at x equals minus b, right? One lattice vector away, right? Except that there's a phase factor. Remember, this is a periodic potential. So it's not exactly equal, up to a phase factor it's equal. So instead of looking at the right, I'm looking back within the unit cell itself. This is why you read unit cells. Spend some time, Breville lattices and everything. This is why you do it, because then once you know the solution within one cell, you know the solution for everything, for the bulk of the material. Okay, so I want a slightly right to the a, and that's exactly equal to something slightly right to minus b, that wave function within my same cell. And therefore, see whether you agree with this statement. What I wrote, that psi at a at x equals a, meaning a minus, a little bit to the left, is equal to psi b, but see the phase factor, e to the power I k p. And why is that? Because I have folded it back one lattice side. I have that equation, and of course I have the derivative equation. The derivative equation again has the little phase factor sitting there. I'm actually done with this because I know the wave functions. I can put them in. Do you see on the right hand side the first equation on the top? Capital A sub A sine alpha A plus capital B sub A cosine alpha A. This is simply by inserting x equals a in the solution of the above equation in the well region, and so on and so forth. You can just match it up. Please take this time when you go home to take this out. I'm going very fast because this is simply algebra. It's not the conceptual point that you need to know, but check it out whether it's correct. I have, how many equations do I have here? I have 4 equations, right? 2 blue, 2 red. How many unknowns? 4 unknowns. You can see B with sub A and B, A with sub A and B. I'm done actually. So if I have that, the step 4 was put them in a matrix. If I put them in a matrix, then how do I find the solution of the eigenvalues? I make the determinant of this matrix equal to 0. And this is a simple 4x4 matrix. How difficult can it be? People could do it in 1930s, and we are more sophisticated, right? So we should be able to do it in a few minutes. And when you do, you get a complex looking equation like this. But just like when we solve for one quantum well problem, it's no more complex than that. Because you can see in this equation, the only unknown is xi, and xi is essentially E divided by U naught. U naught is already given from the material that we have. And there are, of course, lattice spacing involved. There is this A involved in various places. That is something we also know. So the only unknown in this equation is energy level E. And once we solve it, then I know where the electrons sit in a crystal. And how can I solve this? Again, two ways. You can solve it MATLAB, but if you are not in MATLAB age, you can solve it graphically as they do in the book. And let me show you how to do it graphically. And that's where the band structure will come in. So band structure is the solution of the Schrodinger equation in periodic potential, so that we know where electrons can sit. Not necessarily they will sit there, but we will see where the electrons can sit. There's a distinction. There's a distinction between a chair. We are calculating how many chairs we have sort of in a room. We are not still talking about what fraction of them are occupied, So that will come later. And so right now we are just calculating the solution of the Schrodinger equation. All right, let's talk about the band structure. This we should be able to do, and if you please pay attention to this one, because this is where people generally miss it. So let's first plot the right hand side. Remember, we'll plot the right hand side and the left hand side, look at the intersection. Let's plot the right hand side first. Remember that P is given, lattice spacing, and K has discrete values, 0, 1, 2, 3, and corresponding to that 2 pi n divided by np. So when K equals 0, what is the right hand side? Cosine Kp is 1. And that 1, does it depend on energy? 1 is 1. And so with K equals 0, I should draw a straight line independent of energy, because it doesn't depend on energy. What about K little n equals 1? Well, I should then have 2 pi divided by np, right? N is the number of atoms in the string. And then I should have a solution that's again independent of energy, but goes straight all the way through. Now you realize, first of all, that this one would have also been the solution had it been n equals -1, because cosine theta equals cosine minus theta. So wherever the value is little less than 1, but that's straight independent of energy, right? I'm just plotting the right hand side. You can see the right hand side is actually how many equations? This is n number of equations. So right hand side is n number of rate curves actually. It's not just 2, n number of rate curves. Okay, and let's say I'm done. I have spent a lot of time. Of course, you have to draw how many lines? Maybe 1 billion lines, but don't try at home. This is one thing, a few lines would be fine. What about the left hand side? The left hand side is a little complicated, but you put it in any graphical routine, you see that it will go up and down as it moves around in energy. But this time, of course, it's a function of xi, and xi is a function of energy. So therefore, you can see there is an oscillation in energy. Where are the solutions? Solutions are where the rate cuts the blue, because that's when the right hand side is equal to the left hand side. Right? So I'm done actually. I'm done solving it. I'll just have to read off the numbers in a particular way. What I have done simply is rotated it 90 degrees, just like we did in the last class, remember? Rotated it 90 degrees. And let's look at the solution then. So this is K equals 0, right? This red line, the solid red line is K equals 0. And so I'm drawing something with energy in the y-axis, and the x-axis is K. So those are the first 2 points that cut. Not really the first, the ones that I show in the dotted line are the second and the third. You can see there is also a point that cut in below, which is the first point here, very close to energy equals 0. Okay. So this is my solution at K equals 0. For all those electrons that has K equals 0, actually has these energies. Fine. Now what about the next solution? Remember, I have the next line also. And from cutting from that next line, I will pick up a bunch of solutions there also. So I correspondingly shift it to the right, and again blue cuts the red dotted line. Now this time, what is the value of K? the k value is 2 pi over np. So on the right hand side, right hand figure, instead of plotting it as a function of k equals 0, I should shift it a little bit and pick up those points, that is 2 pi divided by np. Do you say this? That will also give me a bunch of solutions. Now remember, k equals plus k and a minus k gives me the same solution. Is that right? So therefore, if I go to the left side on the right hand plot, I will pick up a symmetric point on the other side, just like the first point. I pick up the symmetric point. And this I can continue. How many? Maybe a billion times. I will not do that, but you can see that if I kept doing this, then I will have a bunch of solutions. And these are all these red dots. Now, one thing you will see that I have connected the red dots with the black line. Why did I do that? Because black line means a continuous, that for all k values as if they are a solution. But actually not, right? For red points are discrete. These are not a continuous line. The reason I can do it is when you have 2 pi over a billion, n is a large number, and when you have 2 pi over billion plus 1, then essentially these are so closely spaced that even with a microscope you cannot probably see them apart. So these red lines essentially look like a continuous solution, and therefore many times you will see that they are joined together. People don't put these little dot points. They just simply join together as a continuous point. Now what is the right hand side, maximum right hand side of this k? Remember, it was pi over p, maximum k max and k min. So all the solutions live in this space, and that's why in the x-axis we'll call that region, the k region, is a Brillouin zone associated with the solution. Right? Now electrons can sit in many places, I see, but there are also places where electrons cannot sit, you can see. Okay. Now, how many solutions? Now I'm going to describe to you. We are done with the solutions. We could go home, but rather let's stay with it and try to understand a few features of the solution. First thing is, how many dots do you have in a given band? What is a band? Well, a bunch of solutions which are together. You can see how many bands we have. We have 4 bands of solutions in the bottom, second, third, and fourth. And you can see each is separated by a certain gap. We'll call that band gap. It's a band of solution separated by a gap, so therefore it's called a band gap. And you can see how many solutions do I have. Let's try that. So remember, number of states per band, how many solutions I have. So I'll have to take the maximum region k max and the left hand side minimum region k min. K max minus k min is, you can see 2 pi over p. Do you see on the left bottom side for the graph, the maximum side is pi over p shown here in the red, and the minimum side is minus pi over p shown in the blue. So the difference is 2 pi over p. And 2 pi over p, but the delta k's where the solutions are available is 2 pi divided by np. And therefore, if you divide it up, every band has n points. You see? So why did it come about? Well, remember that every atom, there's, let's say, remember in the square potential, I had first bound level, second bound level, third bound level. When I bring a lot of atoms together, these bound levels essentially all mix together. If I have n atoms, then I have contribution from n of them, and so per band therefore it gets n-fold degenerate, right? There are n solutions per band. It is like potluck, you can have, let's say you do your own cooking at your home, but if 5 people get to the potluck, and then naturally what we'll have is five different type of dishes, right? And if everybody prepared 3, and then you bring them up all together and mix it up, then you can see for each type of food, let's say the entree and the dessert and everything, each type of food, you will have 5-fold. If you had 20 friends, then you will have 20 of them if everybody is really cooking. And it's the same thing. Now, if you had to solve this Schrodinger equation every time, you would be in trouble, because that will be a lot of work. And what we will see that down the road, it's actually not, we don't really need all this information. Different people need different pieces of information. For example, remember the photoelectric experiment? Light coming in, kicking an electron up, and the electron coming out. They shine X-ray on it, let's say. So in that case, I need to know the bottom level all the way to the vacuum level, how far they are apart, all the gaps and everything I need to know. In that case, I really need to know the whole band structure. But many cases in transport, you will see when the electrons are really on the bottom side, they don't really participate in conduction. So for us, many times we don't really need to know all of them, just the ones that are relevant. So we want to capture the information that is over there into simpler things so that we don't have to carry over all this information. So that's what we're going to do now. And that's the properties of the energy band from an electrical engineer's perspective, not from a spectroscopist's perspective. So let's take the question we want to ask now in the next four slides or so is, if an electron was sitting in a band and I applied a field, or I let the electron move, what velocity does it approximately move with? That's what I want to know. How do I do that? Well, I know the solution at every point and its neighbor. So I write it as a e to the power, you can see as an exponent, ikx and minus I omega t. What is that I omega t? Remember, there's a plane wave. With a given k, that wave is moving. If I put at one level, that's the plane wave I'll have at that state. Let's combine two of them. So one is in red, another is in blue on the top. The first one is at k, and the second one is slightly higher at delta k apart. Now when I put them two together, what will happen? Since their k is not the same, their energy is not the same, they will interfere with each other. It's like two lights with two slightly different wavelengths. So they will interfere with each other. And when they do, let's say the red one looks like this. This is a plane wave, right? At a given time, that's the snapshot. And the blue one looks like that. Why? Because the wavelength is slightly different, right? K is slightly different, wavelength is slightly different. So therefore, even if you started them off both at the same point, they will not stay in sync. And therefore, if I combine them, it will sort of, in one place, it will look like it will interfere constructively, and in the rest of the places, it's going up and down all the way, and so it will gradually die off. So I can say, by combining the two electrons, two states, I can say as if I have an electron at that location, right? Otherwise, I don't know where the electron is. It's a plane wave. Where probability of finding an electron is same everywhere in the other case. So by interfering them, I can say where the electron is. Now what will happen a little bit later? A little bit later, you see what will happen is because the E and delta E are slightly apart, or this delta E apart. So what will happen that a little bit later the red one will move to the right, but the blue one will move at a slightly different velocity to the right because it has a slightly different energy, slightly different omega. And so it moves slightly to the right. Now the point where they are interfering is not constructively, is no longer at x equals 0, you can see. They are interfering at a slightly downstream. So as if the original electron which is sitting at x equals 0, that as if has moved down to a certain distance x. And if I could somehow capture this information, then I would know what velocity an electron moves if I put it in a certain band at a certain point. Okay. Now, in order to stay on the peak, what I need to make sure that the right-hand side, the blue side of this equation, that phase does not change with time. So that delta kx minus I delta E h bar multiplied by t, that remains a constant, because then that will have a constant shape that I can follow. Now, I'm sure this step you probably didn't follow. This you have to think a little bit, that y on the peak, and if you plot out some of the wave functions very easily, you can see it numerically. But if this has to be a constant, then I can say that the velocity v is delta x over delta t, right? This is by definition, that at a certain time, how far it moves. Delta x over delta t is the velocity. But you can see from the top, from the blue exponent, that delta E over delta t is essentially can be given by delta E over h bar divided by delta k. Do you see this from the blue? Just do this one step and then you'll see that this relationship emerges. And from here, you can see that the value of a, the acceleration is simply delta v over delta t, which is the Newton's law. Simply Newton's law. Take one more derivative, and when you take this derivative and follow this equation through, you will see that this actually looks like a Newton's law. You can make it look like a Newton law. It's sort of difficult to go through the equation, but it's something I guess you have to just write it in a page. But the bottom line is that you could rewrite it such that the derivative of h bar k, what is h bar k? That's the momentum. Derivative of h bar k with dt. So change in the momentum as a function of time. What is that? That's force. So anything that is left, if I call it n mass, then I can make it look like a Newton's law, as if in a lattice I have an atom, I have an electron, and then I apply a force, and it keeps moving with a certain effective mass, not the original mass. You can see on the left hand side there is no definition of mass at all. There's no notion of a mass at all. There's no m naught sitting here, right? Free electron mass. But only thing that is sitting here is delta E over delta K, that how the solution changes in each of the band, right? So let me show you how it works. It's better to show it with an example. So let's take any two bands. Let's say the third and fourth band. I am not showing the first and the second band. Let's take the third and fourth band. Let's focus first on the red band. Now, velocity, I have told you, velocity is given by delta E over delta K divided by h bar. That's the velocity. If I look at the rate curve, if I change the K a little bit to the right hand side, the energy goes up. So therefore, my velocity should be going up. Do you see? Do you agree with this statement? That if you're sitting on the bottom, then the solution is symmetric on the left and right. It goes through a minima. So when you take a derivative, the value is 0. As you move away from in the plus k direction, the velocity generally goes up, and then eventually it will come down. And similarly on the left hand side, the solution is symmetric. So the velocity would be going negative and then going back to 0. Does it make sense? It should in some way, right? Because remember, with plus k, electrons are supposed to go to the right. And the velocity should be positive because it's going to the right. You can see indeed the velocity is positive because on the right hand side you can see velocity is indeed positive. With minus k, electron should be going the other way. And the velocity should be negative. And it is indeed negative, you can see, right? Because it's below the 0 axis. So that makes sense. What about the effective mass? The effective mass is the second derivative of energy with respect to k. And you can see here, if you take the second derivative of that first equation, then you will get something like this. And you can see that the mass, this particular mass, actually is not a constant. It changes with position because the curvature of the solution changes, and therefore this one changes as well. But the main point is, very close to k equals 0, you can see it's approximately a constant. And we'll use that information later. But throughout the zone, throughout the solution space, of course, it's not a constant, because the solution of the equation is changing throughout. And similarly, you can figure out that for the holes, this should be the opposite. The effective mass should be negative in one case, and the electrons should be going in the other one. So for the blue bands. And implication of this we'll discuss a little bit later. Now, up to this is what is in the book, and you are supposed to know all this. But the professors are very fond of setting the following problem for the qualifying exam. What if you do not have second derivative? What do you do? Generally, at that point, you see the question and you say, okay, today the exam is not going to go well. For example, this particular case. On the left-hand side, I have an energy. By the way, the x-axis is k, the wave vector, right? Remember the solution space? Plus pi over p, minus pi over p. That's the two boundaries of the solution. Now, instead of a straight line, instead of this nicely carved solution, somebody gives me a straight line solution. There is a material called graphene that people are very interested in that has some of these features, at least in part of the zone. It has some of the solution. What do you do now? Well, first thing is that if you try to, we'll look at the equation in a second, so don't worry about it. But first, let's try to see velocity, first derivative of the energy versus k. Well, that's fine, no problem. Because it is a straight line, I can take a derivative, and if I take a derivative, then on the right-hand side, plus k, I will have a constant velocity. On the left-hand side, with minus k, I will have a negative velocity, no problem. Now, what are you going to do when you want to take the effective mass? If you try to take a derivative of this, what will be the derivative? It will be 0. What will be the effective mass? Infinity, right? 1 over effective mass is the second derivative. Second derivative 0, effective mass infinity. Does it mean you pump and you put an electric field and electrons doesn't want to move? Actually, that's not the case. So that very definition of effective mass doesn't hold anymore, because we cannot write the Newton's law as we did in that previous case when you have a continuously carving band. But the solution is still available, because remember what we want to know, that as a function of time, how the energy, how the position and the momentum of the electrons are changing, that we already know from the first two equations. For example, you can see that if the force is the derivative of k with respect to time, change of momentum with respect to time. If I knew the force at a given point, the electric field, let's say coming from the electric field, I could just integrate for that time, for a certain time delta t, and I will know the new k. So it's starting with the momentum, I know the force, so after a certain time delta t, I will know what the new momentum is. Similarly, as soon as I know the velocity, I could integrate the velocity for a little bit of time, and I will know where the electron originally was and where the new electron is, right? So in fact, I do not need effective mass. I can solve the whole problem, not even needing an effective mass, and everything will work out just fine. So variation of this problem are often set just to test whether you understand that effective mass is not fundamental. It is helpful, many times it works. It's a historical baggage. Many modern materials don't have effective mass, but not having an effective mass does not mean that electrons do not move easily through the cathode. In this case, in fact, electrons move very easily through graphene. Right? You see this point? Okay, so it's a long lecture, but let me conclude. So we first said the solution of the Schrodinger equation is easy if we have well-defined periodicity. 80% of the material of interest is not periodic, but it's easy to solve. We'll solve it here, and then for many other material, amorphous, polycrystalline, we'll say, well, I cannot solve it over there, but is almost like a periodic crystal, because most materials are. Now, we said that electrons can sit in narrow energy bands, and not necessarily narrow, in various energy bands, and we showed how to calculate that. And these bands are separated by a gap. So electrons cannot sit everywhere. Remember, we said all electrons are not equal. So therefore, different electrons have different band curvature in which they sit. Towards the bottom, electrons don't want to move. Remember, they were relatively flat. So when you take a second derivative, and when you have the effective mass inversely proportional, the electrons in the bottom band, they don't want to move. These are valence electrons. They don't want to go from one atom to the next. As you go up and up and up, the curvature becomes larger, and the effective mass becomes smaller. Electrons can move through the crystal easily. See, and the final point is that the effective mass is not a fundamental concept. I just emphasize that, and we shall see how to solve K dot P model in real crystals, because this was a fake crystal. One-dimensional, well, what is the last time you saw a one-dimensional crystal in such a simple form? But many of the features of the actual crystal are actually reflective of this very thing. Everybody has bands. Everybody has this Brillouin zone. Everybody has effective mass, if it can be defined. So the real crystals in many ways contain many features which are very similar to this K dot P model, or KP model, or chronic penny model, the people who first solved this problem. Okay, take a look. I skipped a few things, but take a look in your book and understand this clearly. It looks very simple, and I'm sure some of you have read this information before in undergraduate. But to really deeply understand this is very important, because most of these concepts we are learning now, towards the end of the course you will see, and also in other courses, that this is a basis. Most of them don't apply anymore. But if you don't know what are the approximations built into the classical theory, you will not know when they are breaking, and therefore when new theories have to be applied. So understand every assumption with the details, not just glossing over it, right? Okay, thanks.